I'm going to talk about some work that was done by my PhD student Simon Moras, jointly with Hugo Gimbert and myself, who were both co-advising him. So in 2017, I was teaching a course at Collège de France on a chair for 1 year. And for the initial lecture, I had to send some invitations. And I sent one of them to someone I used to know, who used to be in my department as a computer science junior researcher when I was a professor, and who had become the head of cabinet of the Ministry of Higher Education. So I said, Philippe, would you like to come to my inaugural lecture? So he answered, he said, oh, sorry, I wish I could, but I'm too busy. Now we are dealing with a new modification of a college assignment. Admissions to college admissions. And I answered, oh yes, I'm going to say a little bit about stable matchings in my inaugural lecture. And he answered, he said, oh, you're interested in this? So we had a little exchange about this. And then he said, well, if you're interested, would you be interested in working with us a bit? And I said, actually, I tried when I heard about it. I sent an email, a polite letter to some person at the ministry, and I never heard back. And he said, well, that was a mistake. Come. So I started consulting with them 1 day per week about the algorithmic aspects of the college admissions practice for about 2 years. And this was the first time I had done anything that was not purely theoretical, so it was kind of revolutionary for me. And I discovered all my values, my dimensions, were not aligned with the rest of the world. But anyway, so it did bring up some interesting questions, and one of those questions led to the center, the core of Simon's PhD. So I'm going to tell you about what we did during that time. So it's about Gale-Shapley, which is the basis of the college admissions method. We are looking at matching universities with candidates, and we're taking the university proposing viewpoint on or side of Gale-Shapley. That is, at every step, universities propose to their favorite candidates to whom they have not proposed yet. Then every candidate looks at their option and accepts their best option and declines the rest. And then you repeat, update and repeat, with the big caveat that this is deferred acceptance, that is, candidates can change their mind over time. Refusals are final, but acceptances are not final. So this is an example where you have 3 universities, UVW, each of them has capacity 1, and it's an example of execution. In red, the candidates who refused. In green, the candidates who accepted a proposal. And in yellow, the candidates who received a proposal are receiving a proposal at that round, and they haven't answered yet. Okay. So this is basically the algorithm that is run during college admissions in France and in many other countries. This is stable in the sense that there's no blocking pair. There's no pair. For example, here in this particular matching is not stable because A is matched to 3 but prefers 1. 1 is matched to B but prefers A. So A and 1 prefer each other to their mates. So that makes the matching unstable. Why is it desirable that a matching be stable for college admissions? Because if the matching was not stable, so what happens? University A and candidate 1 both think, had I known, we would have done this matching differently. And what happens on year N+1? University A, instead of telling the ministry, we have 30 slots, tells the ministry, we have 25 slots, keeps 5 slots for themselves. Then they wait to see what happens, and then they're going to take 5 students outside the algorithm and tell them, come. And these 5 students, if this is better than their current match, they will say, okay, we'll come. Repeat this a few years, and the platform no longer works. So it is widely considered that stability is a very desirable property for a platform to work in the long term. Manipulability. So here, if you look at the preferences of universities UVWX, look at candidate number 4. So after you've run Gill-Shapley, the result is University U has made offers to 1, 2, and 3. 1 and 2 said no, 3 said yes. That's the outcome for you. V got their first choice, candidate 1. W made offers to 1 and 3, and finally to 2 who said yes without changing their mind. X got candidate 4. And this is, this is the outcome of Gill-Shapley that can also be described with a threshold. Okay, now look at candidate number 4. Can candidate number 4 somehow change her answers to obtain a better university than X, a university that she prefers? To know her option, there could be a first phase where she just learns what happens by rejecting all offers. So imagine everybody else answers according to Gill-Shapley, truthfully, but candidate number 4 is going to just reject all answers. Then, so you start from the Gill-Shapley optimal matching. Her match is X. Then if she refuses and it continues, you can see that she has the option of getting a slot at University V, because University X says, oh, I didn't get my candidate, then the algorithm continues, because X continues looking for additional candidates, and then other candidates will change their mind, and then the algorithm is not really finished. XV, then 4 rejects V again, says no again. And the algorithm continues and eventually gets an offer from W. Okay, great. Then says no again and sees what happens, and what happens in the end gets no offer. Okay, so if she rejects everything, eventually she gets no offer, so now she knows. Her options are X, V, W. So what is she going to do if she knows what's going on? She will pick her favorite answer, her favorite university among X, V, and W, and during the execution of Gill-Shapley, she will say no to every offer except her favorite. Okay. And that's how she can manipulate Gill-Shapley. Assuming, of course, she has perfect knowledge. Yes?
Yes, but in Gill-Shapley, when X proposes to student number 4, she tentatively accepts.
Yes.
But in the end, she will get the proposal from V and W later on in the algorithm, right?
Well, the problem is the stopping condition. When does the algorithm stop? When nothing happens for one round. Yeah. So if you look at this, what I call step 6, 3 tentatively accepted U, 1 tentatively accepted V, 2 tentatively accepted W, and 4 tentatively accepted X. At that point, all the universities think they have filled their slots. The next step, nothing happens, and at that point, the algorithm stops and says all the tentative accepts, they're the final accepts. Okay, so I forgot to say that. That was an important point. Thank you. Okay, so if you look at the collection of all possible stable matchings, they form a lattice structure. So for the input I lined up here, you can see this structure. On top, there's the Gill-Shapley University proposing stable matching. It's a matching where each university simultaneously has their best possible stable partner. So here, these are all universities of capacity 1. No, I call them universities and candidates, but universities have capacity 1. Okay. And at the bottom, each university has their worst possible stable partner, and each candidate simultaneously has their best possible stable partner. Okay, so there are 2 ways to run Gill-Shapley. I mean, it's hard to get to the matchings in the middle, but if you want the top or the bottom, it's easy. You run Gale-Shapley university proposing, or you run Gale-Shapley candidate proposing. Okay, so when the algorithm for college admissions was discussed in many papers in 2018, when it came to Alive, there were many complaints about this. People said, university proposing. So you end up with the best possible assignment for universities, well, if capacity 1, but the worst possible for the candidates. That's not right. You know, in a well-designed system, you should do the opposite. You should run your algorithm to get the student proposing best outcome, the best outcome for the students. Okay, so to summarize the manipulability, the university optimal Gale-Shapley algorithm produces a stable matching such that every university obtains his best possible stable partner if the capacity is 1. That is, no university may obtain a better outcome by lying about their preferences if the capacity is 1. And candidates, on the other hand, may obtain a better outcome by lying about their preferences. Okay. So people said, you know, it would be much nicer if the candidates could just get their best possible offer by running the candidate proposing. Now, people in the ministry didn't want to do that. They didn't want to do that I think for 2 main reasons. One is psychological. Imagine you run, so this is all run in real time, in you know, human questions and answers. Imagine you run the candidate proposing Gale-Shapley. Round 1, May 23rd, 2018. All the candidates send a request to their top university. Then, May 24th, every university answers. Either they say no, or they say yes, but I might change my mind later. So now imagine the candidate. On May 24th, they think, oh, I have my best choice. And then a week later, the university contacts them and says, oh, no, you know, we got a better offer that we like better, we don't take you. Not so good. I mean, it was felt that it was better to have the candidate situation gets better and better over time during execution, rather than it get worse and worse. See, if you do candidate proposing, the candidates keep going down their preference list, and every time they get a reject, they go down to the next one. And then somebody says yes for a while, then they say no, we go down to the next one, and so on. So over the execution, things just keep getting worse and worse. Whereas instead, if you do the university proposing over time, the candidate just has more and more option, and at any time, what they pick is the best of all the options they received. So it seems somehow better, like forward-looking. Okay, so this reason is, you know, you can find many faults with it. There's another reason that I think is much stronger, which is that in reality, so Gale-Shapley is a static algorithm. You have the input, you produce the output. In reality, everything is shaky. That is, university capacities. You know, maybe you can find some money at the last minute if you realize that some place is really in high tension. Many, many people want to go there. Maybe you can find a little bit of extra money to give to that university to convince them to open an extra group, you know, and to admit 30 more students. Students, maybe they leave the system. They say, oh, I don't want this to do this after all. I'll do something else next year. I'm going to Oxford, or, you know, to work in the fields somewhere in northern Italy. So students leave the system, and what happens in the university proposing Gill-Shipley when students leave the system. If a student leaves the system, it's as if they said no. So it's naturally incorporated in Gill-Shipley. It's like a student said yes, you thought the algorithm was finished, and then they say, oh, no. So they disappear, and then all you have to do is restart the algorithm, continue, because the ending condition is no longer filled. Okay? So it's very simple to adapt Gill-Shipley to the setting where some students leave, the set of students decreases over time. Or maybe some students will not pass baccalaureate. So on the day when the results of the baccalaureate come in, some students fail, 5% of the students. When they fail, they can no longer go to a college. And then that creates some empty slots, and then you can restart the algorithm. Okay. So for various reasons, yes?
That strategy doesn't work if the student is obliged to accept some offer.
How do you force someone?
Changing mind later, right?
What?
So the strategy can work if the student is obliged to accept an offer.
Yes.
With the possibility to
change their mind.
Change their mind later on, right? So it must admit the possibility that the student doesn't get any position. Of
course.
Okay.
There is the possibility that the student doesn't get any position. That happens every year. It's also the subject of many papers. Many articles in the press. Yes?
Maybe there is like another reason that on the large markets we can have just one, usually there is only one stable matching. So the authorities don't care like whether you use college proposing or student proposing. If they have college proposing not working and the matching is the same, why change?
That's right. That's right. So this is another reason, but they didn't really realize it at first. But then this is what happened in practice. Empirical studies by Roth and Berenson on the resident matching program in the US, done with Gill-Shipley. The set of stable matchings and the opportunities for strategic manipulation are surprisingly small. Why is that? There's a small explanation, a beginning of an explanation provided by Demange, Gale, and Sotomayor. The observation that if a candidate has only one stable partner, then they cannot manipulate. If you look at the lattice, you can look at all stable matchings. You focus on one particular candidate, you observe which university they got in all the stable matchings. If it's the same one, then you cannot manipulate. The candidate can say no to that offer, but then they're stuck. They won't get anywhere. They won't get anything. Okay? So if a candidate has only one stable partner, they cannot manipulate. Then we took a look at some data from APB, the predecessor of Parcoursup, to take a look at the manipulation. So because of that, how many students can manipulate? How many students can have more than one stable pair? Okay? So what you do is you take your data from 2016, you have all the preferences of everybody, you run Gill-Shipley continued. So for each candidate in turn, you run Gill-Shipley, and then you start saying, oh, actually, they're going to say no to everything. So we look at all their stable partners. So we do that for everybody. And then this gives us the number of people that have more than one stable partners. Yes?
What was the algorithm in APB?
Gill-Shipley.
The school proposing?
Yes.
So how do you know they are not already manipulated, these preferences? You take them as
we take the input as though it was the truth. Yes. And we look at, for that input, we look at what happens, the number of stable partners of each person. And what we observed was that the number of people who had more than one stable partner was ridiculously small.
But then, if everybody manipulates to get their favorites,
Yes.
they are already truncating their lists.
Yes.
You think there is only one partner, but it's because they are already manipulated.
That's true.
How long are the lists? How big are the lists?
Okay, so yes, I presented this with a full list, but actually the students only don't apply to 13,000 places. They only apply to maybe a dozen, maybe 20. You know, it's limited, but with the various rules, you can end up applying to maybe up to 50 places with all the vœux, sous-vœux, and so on. No. So, and on average, maybe about 5, I forget. No, I forget, 5 to 10. No. So yes, Julien, I take your point. You're saying maybe the students have already optimized their behavior under APB. They already knew how to manipulate to get their best possibility. Meaning, for that algorithm, that means not applying to places where eventually they will not be.
Especially that during APB, there was also one very, very strategic thing, which was that your first choice had a bonus of priority. So
yes.
This
yes.
really gives you incentive
Yes.
to report to target the ones you think you will get as a first choice.
Yes.
And then you'll set up
So what is called APB, Admission Post-Bac, was initially designed, very well designed. It was the introduction of Gilles Shipley for college admissions in France. It was done for prep schools, very successful, so it was extended. And then people started thinking of improvements. And one of the improvements was universities said, you know, we care about, we would like to have students with good grades, if possible. Of course, we don't know. But really, we want students who are motivated. And what is an indicator of a student being motivated? It's if they put the school as their first choice. Okay. So let's add a rule to add something to the university preferences to give put the students who put that university as a first choice ahead of the others in the ranking. In other words, the ranking of the candidates by the universities was a function of the ranking of the universities by the students. The ranking of the candidates by the universities was a function of a ranking of the students of the universities by the students. The result is, from a theoretical viewpoint, it's no property holes anymore, because now students have a high incentive to manipulate the matching, their preference list. So the preferences they enter, they're advised by their teachers who have some knowledge of what's been going on the previous years, or by unions, parent associations. They're advised to lie about their true preferences. So this is the data. It also, it resulted in much anxiety, I think, among the students, because they thought, what should I enter as my preferences?
Just to come back to this, because you are checking the number of stable matching afterward, this type of priorities, they also create top pairs, right? Like students who rank the school first.
Yes,
so
yes.
if it's truly top pairs everywhere, then the matching the stable matching is unique.
Of course, yes. If everybody's first choice, if all the first choices are mutual, then you're done right away. So, this is maybe part of the reason why APB was, so many people got their first choice. Okay, so at least that, so the creator of APB, I am told, was very unhappy with that patch because he knew that was not a good idea. But, the designers didn't know. So that's why it's good to have academics be present to help with the design of those systems. Okay, so let's try to explain this lack of manipulative theoretically. Julien gave an explanation in practice. Now let's try to see if we can, if we believe there are very few stable partners, let's try to find an explanation. Okay, what happens on average? What happens on average if everything is, every preference is a random permutation? So I go back to the theoretical world. Then, university proposing, a university gets approximately a candidate that has rank about log n in their list, and a candidate gets a university that has rank approximately n over log n in their list. And if the candidates know how to manipulate, then they can raise their ranking from n over log n to log n. It's a huge difference. So in the random case, actually, people have lots of stable partners. There's a big opportunity to manipulate, and you can really, as a candidate, you can really improve your situation by manipulating. So this does not reflect what was observed by Roth and the other people on the resident matching program. It does not reflect what was observed on APB. So, not a good model. Also, independent, random, uniform permutations, that's not the reality. That's not the real world. So, we wanted to add some assumptions, so go to something that was beyond worst case, so that we could say, if some assumption holds, then, so several possible conclusions. One ideal conclusion would be every candidate has a unique stable partner. Then no manipulability. Second possibility, if some assumption holds, then almost everyone has a unique stable partner. So very few people can manipulate. Third possibility, if some assumption, then for almost everyone, the stable partners are maybe not unique, but they're close to being unique. I mean, they're ranked around the same area of the student's preference list. So you can't go from n over log n to log n by manipulating. Okay. And so this was part of Simon's thesis, was to find how to define these conditions so that those conclusions would hold. Okay. If all universities have the same preference list, then the stable matching is unique. Why? Because just run the, let's see. Because candidate 1 is every university's preferred best choice. So candidate 1 must be matched to her favorite university, otherwise it's a blocking pair. Remove candidate 1 and the favorite university of candidate 1, and iterate by induction. That's the unique stable matching. Okay. Approximate non-manipulability in terms of almost everyone having a unique stable partner. That was partly addressed by Ashlagi, Canoria, and Leshno by saying if there's a little bit of unbalance, then you're good. That is, if you have one more candidates than universities, the number, every university has capacity 1 throughout this talk. If you have just one more candidate than university, and everything else is random, it's the setting studied in the last previous decades with random uniform permutations, then if you compute the total number of stable partners, it's n plus a little O of n. Meaning, on average, each candidate has one stable partner, meaning almost every candidate has one stable partner. Amazing. So just one slot missing means there's enough. It creates some competition. In this case, there are too many candidates. Candidates have to compete to get into universities. One of them will be left out, and that's enough to make this the result, regardless of which version of Gale-Shapley you run. That's enough to get the result university optimal, essentially. Sorry. Third, the topic we focused on more, popularities. The intuition is the rankings are not independent. There's some correlation between rankings. For example, if you look at how universities rank students, if you have two students, one of them clearly has better grades than the other, and they come from the same school, let's say, then the universities will usually, almost always, rank the first one above the second one. So the rankings are correlated. Yes?
Does this depend from the order in which the university is proposed? Because if they have all the same...
This is not about the algorithm. It's about how the preference lists are defined.
Okay.
So how do universities, they receive all the folders, they rank the students. If all the universities have the same ranking, unique matching. If they don't have this, if they have independent rankings, a lot of things can happen. But they don't have independent rankings in reality. Some students are clearly stronger than others, comparable, and then, all the places where they both apply, student 1 will be ranked ahead of student 2. So there's correlations. Similarly, there are some settings about school reputations. Many of you, among the ones among you who are French, many of you have done prep school. Then you have, done a competitive entrance exams to some schools, and you know that in these grandes écoles, there's there's sort of a ranking, that is, nobody is going to turn down. What? Nobody is going to turn down ENSAI to go to. All right. So Roth and Perensen they also observed in the resident matching problem was that there was correlation of preferences among programs on one side, among applicants on the other side, and observed that when preferences are highly correlated, the set of stable matching is small. Okay, so that's our assumption. If universities have highly similar preference lists and candidates have highly similar preference lists, then maybe, yes. Then maybe the stable matchings are, there's few of them, few stable partners.
Yeah, sorry, on that, so if ranking of universities are the same, then I don't need to assume anything on candidate side, and I know the stable matching will be the same. So
That's
here
right.
you will say both have correlated preferences. So I'm just curious to know if you drop one of the two sides to have correlated preferences, do you know what happens here? Or
Yes, actually, we started with both sides, then we worked, then we got a proof, and then Simon said, well, actually, we don't need one side, we only need one side.
Okay, yeah, I see. So that's the intuition that...
Yes, yes. Okay. So we use popularity preferences that in the world of computer science was introduced by Luca and Madian in 2005. Each, let's say, university has a popularity, a reputation, a Shanghai ranking, or whatever, something. Okay. And then the student who doesn't know any better is going to just use these popularities to create their ranking. What do? They take a bag, they put the universities in the bag, and then they pull the universities out of the bag proportionally to their popularity, without replacement, of course. So the first university will be taken with probability proportional to PA, PB, PC, PD. The second one among the remainder, and so on. So for example, what is the probability that you get the student has the ranking, the preference list, D, C, A, B? Well, the student has to first pull out D with probability proportional to P sub D. Then D is no longer there. Then the second one is C. It needs to pull out university C among the remaining. Then A among the remaining, and then B among the remaining, PB over PB. Okay. So that's the probability that you create this ranking. So, and every student does that independently. So if you think about this, imagine the case where all the popularities are equal, 1 over n. Then what happens? This is a random uniform permutation. Case number 2, the other extreme case. Imagine PA is infinitely greater than PB, which is infinitely greater than PC, which is infinitely greater than PD. Then every student will get the ordering A, B, C, D. Okay? And then you can, so perfect correlation or no correlation. And then you can play with these popularities to get intermediate states. We're going to focus on a geometric example because that's what that captures the main ideas. So we assume the popularities of universities are 1, 1/2, 1/4, 1/8, and so on. Then there's a kind of a generic preference list, which is A, B, C, D, ordered by preferences. And if you think about each student's preference list, it's going to be very similar to that master list A, B, C, D. You know, there will be some switches here and there, but not very much, not very far. You know, every ranking will be close to A, B, C, D. What then is the structure of stable matchings? The answer is, for each candidate, if you look at what happens in expectation, you will find that all of its stable partners are close to one another in the list. That is, if you look at how she ranks her best stable partner, her favorite stable partner, and her worst stable partner, so what she gets from university proposing Gale-Shipley and what she could get by manipulating as best as she can, well, these are only separated by a constant, at a constant distance from one another on average in her preference list. So this is sort of an explanation why manipulating doesn't help. You know, it's 1 degree, it's approximate non-manipulability. Manipulability can only gain you a few slots in your preference list. Now remark, it's only assumptions on one side. The generalization is, so after we prove this, Simon tried to extend, and so here is, here's a theorem that appears in his thesis. Let's say that the distribution is regular if you think about the preference list. On this preference list, you already have some partial information. For example, you already know that B, so that the candidate prefers B to C, C to D, D to E, and E to F. What does that tell you about B's position, ranking, compared to all the other universities? Well, B is the best among this subset. Conditioning on this can only help. No, it can only increase the probability that B is ranked ahead of each of the other universities. Okay? Because it wouldn't make sense to say, I know that B is ranked better than C, Therefore, B is ranked lower than A, even though if you didn't have that knowledge, B would rank ahead of C. Okay, so it's a very natural assumption. Okay.
Is this implied by the model that you had before?
Yes, it's implied by the model, but it's more general now. Now we're switching to a more general model. It's also true in the matrix model where you had the AIJs, all the preference lists were used not popularities, but a different, instead of having P sub A, you have P sub IJ, for candidate I, university J. So it's also true in that model. Okay, so on one side you have a regular distribution, on the other side it's arbitrary. And let's look at the odds that there's a switch between university I and university I plus K. There's a particular ordering of universities. So that there's a switch between two universities that in the master ranking are a distance more than K from one another. Okay. So let's look at these odds that there's a big switch. If you can compute these odds or upper bound these odds, then you can deduce an expression of the span of the stable partners. Look at each candidate that has a stable partner. Look at where all the other stable partners are. There's a formula for the span. So in the case of a geometric distribution, it gives you big O of 1. Okay. So that's what I meant by the stable partners are ranked roughly the same. There's a little more theory there. Now let's make assumptions on both sides. One side, geometric. The other side, random uniform permutations. Then, almost every person has a unique stable partner. The total number of stable partners is n plus little o of n. Okay, so that's kind of a cute theory observation. Nothing to do with reality, of course, but it's another setting. Okay, with a generalization, which I will skip. Now I want to give you some proof because that's what we're here for. Let's prove the geometric result. Let's look at the special case. So, for some reason I switched to men and women. So I'm going to try to translate this as I speak. I have finally decided to give up on the men-women terminology. So I'm going to try to talk about university and candidates. Universities are the men, candidates are the women. Okay, so the universities' popularities are 1, 1/2, 1/4, 1/8, and so on. Then every candidate's preference is similar to A, B, C, D. Okay, so analysis. Look at the universities, ordering them from most popular to least popular, 1, 1/2, 1/4, 1/8, and so on. Compute the university optimal stable matching. University proposing Gill Shipley. You get a particular matching. The ordering on universities induces an ordering on the candidates by looking at the partners in this university optimal stable matching. Now in here, we draw a line. We call it a separator in this graph. If every candidate above the line prefers their partner to every university below the line. For example, candidate 2 prefers university B to all the universities D, E, F, etc. Okay. So that's a definition of a separator. What can we say about a separator? If this is a separator, in every stable matching, universities A, B, and C must be match to the set of candidates 1, 2, 3. Okay, so there can be other stable matchings, but they all have to map the set ABC to the set 1, 2, 3. Why? Because otherwise there's a blocking pair. Should I give the proof? No. Okay. Repeat. So you find your first separator, then the second separator. Look at all the separators. Now what we have what we call a block. A block is what? The set of universities and candidates between two consecutive separators. What can we say? In every stable matching, the block as a set maps to within the block. So this gives us a lot of structure about stable matchings.
How do you know that they are separators?
How do I know that they exist?
Yes.
Well, in the case of geometric popularities, I mean, in the worst case, there's just one, which is after the last university, and the block is everything. But I'm going to prove that in the case of geometric popularities, these blocks exist and are small. Okay, so let's focus on candidate number 2. She's assigned to University B. Her block is Universities B and C. Her stable partners are a subset of BC. Let's look at her preference list. For example, B, A, F, C, D, E. Oh, actually, this is false because this means she yeah, this is good. She prefers B to D, E, and F. Okay. So let's say that her stable partners are both B and C. The difference in rank between B and C in her preference list is what? It's at most the size of her block plus the number of universities that are inserted in her preference list in between the universities of her block. Okay? Like A, morally A should be ahead, but actually there was a switch. A is ranked second in her list. And F, you know, if you look at popularities, F should be last, but actually in her preference list, it ends up being squeezed between B and C. So this increases the distance between her stable partners. Okay, so that's how we can bound the, the difference in rank in her preference list between the best and worst stable partners. The size of a block plus the number of inserts that don't correspond to the master ordering. Okay, so let's first look at the inserts. Let me look at candidate W, look at her block. See the block? There's the block. The top university in her block is M0. The bottom university in her block is M3. But if you look at her preference list, you know, you go in the order of her preferences. The first one you encounter is M1, you know, because maybe there was a switch between M0 and M1 when she created her preferences. And the last one is M2, not necessarily equal to M3 because maybe there was some switched. And all of the block is between M1 and M2. Now, there are two kinds of inserts in her list. The inserts that come from more popular universities that accidentally got ranked after M1. And so let's think about this. Geometric preferences. What are the odds that, you know, this university got ranked above M1, after M1? So it has to switch to be ranked after M0. That's at most 1/2. Then this university, the popularity, you go doubles by 2 doubles every time you go up. This university, probably 1/4 that it's inserted, 1/8 that it's inserted. Altogether, a constant number on average. And what about the less popular universities? What is the probability that they're inserted? It's the probability that they pass M2. You know, they are ranked ahead of M2 even though they're less popular. By the same reasoning, it's a constant number. So the number of universities inserted in between, order 1. Okay. Now, let's look at the size of the block. So, observe that once you have defined the first block, in every stable matching, all of the universities in the first block are mapped to all the candidates in the first block. And so this part is kind of irrelevant for the rest. So what this means is that we can use induction. By induction, we can just analyze the size of the first block, and this will hold for every block. Okay, so to construct the first block, so let's do some attempts. These dots are attempts. Let's attempt to draw a separator. So the question is, where is the first separator? A separator after the first line, after AW1. When is it a block? Well, the question is A W1's favorite university? If not, we don't have a block. So let's look at the universities that W1 prefers to A. Maybe there's B and D. So in that case, this cannot be a separator. Not only that, but the first separator cannot be above D. So the next candidate separator is, we draw the next line just below D. And now we think, is this a separator or not? So from the viewpoint of W1, we know we're good. So now let's look at the partners of B, C, and D. Who do they prefer among the rest to B, W2 to B, W3 to C, W4 to D? Let's look at these edges that cross, these preferences. And maybe we find that W3 prefers F to C. Okay? And this is the edge that goes farthest down. So we look at these 3 candidates. This is a new, we haven't looked at them yet. And then we look at how far down their preferences go. Okay, so F. So this means the next candidate separator is here, and so on. And then eventually it succeeds, and then we're done, and that defines the first block. Okay, so now we can analyze this algorithm to find the size of the first block. That is, the candidate separators, we jump, +3, +2, then we're done. So plus something, plus something, plus something, a certain number of steps, a certain number of times. Observe that because it's a geometric distribution, every time you have a candidate separator, you have a constant probability bounded away from 0 that you're done. Okay? So the expected number of iterates will be order 1. And in each iteration, how far down the list do you jump? Again, because of the geometric distribution, on average, you only go down order 1 steps. So each step has a order 1 length. The number of steps is order 1, so the total is order 1. So the block size is order 1 on average. Okay. So to analyze this, you have to take advantage of some independence, create the candidates' preference lists on the fly so that you have some fresh random bits so that your analysis is correct. Okay, so that concludes the geometric example, and it concludes the proof of the difference in rank between the best and worst stable partner. Okay. Okay. So what was the method used here? We started from a real life or intuitive observation on something we're interested in, say manipulability. So we started from that sentence in that paper that said, the opportunities for strategic manipulation are surprisingly small. Surprisingly, that's the word that catches our attention. We care about manipulability, and there's an observation that is surprising. then we say, oh, doesn't work in the worst case. Oh, the observation doesn't hold on average either. So let's create a beyond worst case model and prove something that matches the observation. And then after that, it's time to step back and look again at what we proved, look again at our model and say, do we like this model? Do we like this model? Is this reasonable? In some sense, it's reasonable. On the other hand, if you think about universities, they don't have capacity 1. They have large capacity. So I think one aspect in which this theorem is, can be criticized, I mean, there are many reasons, but one aspect that I think is particularly important is the fact that we dealt with capacity 1 throughout. So it might be nice to look at some kind of similar thing, but with large capacities. And with this, I will stop. Thank you.